Hello, this is Lazarus at telecomTech, where telecom and networking technologies are simply explained. Today we'll be simply explaining the role of AI in wireless antenna architecture. We usually think of antennas as simple passive metal structures, but what if they could think? AI is quickly becoming part of the antenna system in both mobile networks and Wi-Fi networks. We usually think of the antenna as a passive component, but AI is quickly changing the role of this humble part of wireless communication networks. We know that AI has already become a critical part of network monitoring and management systems. AI-assisted network monitoring systems ingest a whole series of network metrics and are able to proactively respond by automating adjustments to routing policies, QoS behaviors, and traffic steering. Antennas are now becoming an active part of this AI ecosystem, especially within mobile networks in the area that we call the radio access network, or the RAN. This evolution towards AI-driven RAN architectures was recently showcased as one of the most innovative developments at Mobile World Congress in Barcelona. This is part of a broader industry shift towards what's being called AI RAN, where artificial intelligence is beginning to be more deeply integrated into the radio access network itself. Think about this. According to an RF engineer from a notable mobile network equipment vendor, a 1% tilt deviation of an antenna could result in a decrease of up to 25% in throughput on devices at the cell edge. And when you have hundreds of users throughout a cell, such a deviation can cause a substantial aggregate throughput reduction, which is a major network event. And all of that from just a 1% deviation. This degree of deviation over time is expected in an antenna installation because it can simply be a result of extended wind loads or due to the expansion or contraction of the materials of the tower on which the antenna is mounted, or it may simply be a part of the margin of error during installation. To deal with such issues, it will first take a site survey to detect it initially, a repair crew to be sent out to fix it, and then another site survey to check the results. All of that takes time and money, and until it's done, the cell will be experiencing its 25% degradation, affecting hundreds of users. Now imagine that the antenna has appropriate sensors, including gyros that can detect a fraction of a degree of tilt degradation, high-precision GPS systems, and sensors that can measure wind load to a high degree. All the information that's gathered by those sensors can be sent to a centralized or a distributed AI system, ingested, analyzed, and processed. The system then sends back commands to the antenna to fix the tilt using onboard actuators and restores maximum coverage. What would have taken days or weeks to detect and remedy, and would have cost a lot of money, can now be done in a matter of seconds. A truly self-healing network, even at the antenna itself. Now, for those of you that are familiar with wireless technologies and how radio frequencies behave in free space, you'll know that the tilt of an antenna is not the only thing that affects optimal coverage. Continual changes, both short-term and long-term, in the environment around the antenna can affect the way RF signals propagate and how they are distributed. Changes in temperature and humidity affect how signals are distributed through space in the short term. The changing landscape also affects RF signals. Deciduous trees in winter have no leaves, while in the summer their leaves become barriers for RF signals. These are seasonal changes in the environment. Or a new building is built near a cellular base station, and this changes the whole distribution of RF signals due to reflections and refractions, and this represents a more permanent change in the environment. All of these changes affect RF coverage over time, and small adjustments to the antenna, its tilt, its frequency range, its power output, can optimize coverage as these parameters change around it. With information gathered from the appropriate real-time measurements from sensors on and off the antenna, and having that information ingested by an AI system and analyzed, commands can be sent back to the antenna to make changes in real time to various parameters, ensuring that the RF distribution remains optimized. Now, before I continue, I'd just like to say that this video is sponsored by XOP Networks, provider of emergency communications phone systems for airports, power plants, and disaster relief organizations. Learn more at www.everythingoverpackets.com. This approach is a real game changer because the antennas are now designed to provide visibility into the localized conditions of the RAN. And this in many cases could be the difference between optimizing your existing base stations and being required to install a new base station. Of course, it's preferable to achieve optimal coverage with the existing base stations rather than having to incur the cost of installing a new base station, which requires equipment, licensing, installation costs, and maintenance costs, all of which will eventually trickle down to the end user. And when you consider that a large RAN deployment can include thousands or even tens of thousands of these base stations in the whole network, you can immediately see the benefits of such an arrangement at scale. So antennas, which were traditionally passive components of the network, are quickly becoming an active part of the AI ecosystem of network monitoring by collecting vital information necessary to automatically respond to the changing environment. Now, although this technology is primarily being used in the cellular RAN environments of mobile networks, like 4G and 5G networks, the principle is valid to be used for Wi-Fi networks as well. For Wi-Fi, instead of physically tilting antennas, AI can dynamically adjust transmit power, select the best channels to avoid interference, steer clients to better access points, and optimize beamforming and MIMO behavior. And this can be done not individually on each access point, but holistically on the whole network, ensuring RF optimization throughout the whole area covered by the network. We're moving forward towards networks that don't just carry traffic, but they adapt and learn and optimize themselves in real time. And this is just one more example of this innovative and exciting trend of incorporating AI into network monitoring and management. So what does this all mean? It means that networks are no longer just static infrastructures. They're becoming intelligent systems, systems that can sense, learn, and adapt in real time. And we're seeing a shift from static RF design in the RAN to dynamic AI-driven radio environments. And antennas, which were once simple passive components, are now becoming active participants in that intelligence. And this is a big shift. Because instead of consistently building more infrastructure, we can start making our existing networks smarter, more efficient, and more responsive to the real-world conditions around them. And honestly, this is really just the beginning. Now, if you found this interesting, please let me know in the comments. Also, check out my website at telecomtech.io, subscribe to the newsletter, and subscribe to this channel. I look forward to seeing you now and in the future. This is Lazarus at telecomTech. I hope this video has been helpful for you, and I'd like to thank you for watching.